Okay, also ich habe jetzt angefangen, das aufzunehmen. Okay.
Mhm.
Ich muss nicht vergessen, das am Ende das wieder zu stoppen.
Ja.
Ich gucke mal hier.
Was ist das?
Das ist, dass Luis etwas machen will. Wie kann ich lassen, dass er spricht?
Ach so, musst du das einstellen, dass die bei den anderen, oder?
Ich versuche, ich mache ihn kurz Moderator. Luis? Ich bin nicht sicher. Eigentlich kann er jetzt...
I don't...
Luis?
¿Sí?
Sí, ¿tú puedes hablar?
Sí, ¿me escucháis?
Sí, sí, dime.
No, que es la primera vez que it's the first time I'm handling this machine.
Okay. No problem.
That's very well. I can hear you. Hello.
Oh, okay. How are you, Andreas?
I'm fine, thanks. How are you?
Okay, thanks. All the family it's okay.
That's nice.
Okay. Well, let's wait.
Okay. So jetzt die Zeit ist Good. So thank you everybody for coming today. We will start again our PhD seminar with a talk from Andreas Jung from the University of Trier, who did a research day 4 years ago working together with Luis Bernal Gonzalez. And he's gonna talk today about simultaneous hypercyclicity. Now I will please mute all your microphones and shut off your cameras. And if you have any questions at the end, please click the button to raise your hand. Thank you very much. So, Andreas?
Okay.
Buenas tardes. Muchas gracias, Pablo, por la introducción. Me llamo Andreas, soy de Alemania y de la ciudad de Treveris y tengo 32 años. Estudié matemáticas en la Universidad de Treveris, especializado en análisis, y también hice mi doctorado en la Universidad de Treveris, especializado en análisis complejo. Sobre todo investigué hypercyclicity de operadores de composición. El segundo supervisor de mi tesis doctoral fue el profesor Luis Bernal González, y después de mi doctorado tenía la gran suerte de poder pasar un medio año con él en Sevilla en 2016-2017 en el marco de una beca de investigación. Y hoy quiero presentarles unos resultados de nuestro trabajo científico de este tiempo. Now, two things happen at the same time. Not only my presentation language changes to English, but also, as you can see, the text on my slides will be in English from now on. Although I do like the Spanish language very much, I think it would take me many more years of study until I would be able to give a complete talk in Spanish, or in particular to understand any questions from you in Spanish. So please feel free to ask anything at any time in English. I hope this is possible. If you can just unmute your microphone, and then you can ask me anything at any time. Okay, so what is this talk about? As the title says, it's about the concept of simultaneous hypercyclicity. And now on the first few slides of the presentation, I first want to give some introduction and motivation into for this new concept. And I want to start with some very general background, which are discrete dynamical systems. In its simplest form, discrete dynamical system, I think, is given by a set X and a self-map T on X. The set X can be interpreted as the space of all possible states of the system. And the map T can be seen to, let's say, describe the temporal development of the dynamical system. For the notation, if you consider an initial state, so a point small x in the set X of the state space, then we denote the state of the system at time n, where n is a positive integer, by Tnx. So here and throughout the whole talk, Tn always denotes the nth iterate of the self-map T. Typically, one is interested in the long-time behavior of the sequence of iterates Tnx for arbitrary initial states x as the time n increases. On the one hand, it might be possible that for some initial states x, the dynamical system behaves stably, meaning that the sequence of iterates Tnx approaches some kind of state of equilibrium as n increases to infinity. On the other hand, it might also be the case that for other initial states x, the sequence of iterates behaves unstably, or let's say the sequence of iterates somehow shows a chaotic behavior. Chaotic means here, roughly speaking, that tiny changes of the initial state of the dynamical system could lead to completely different long-time behaviors of the system. In combination with keywords such as the butterfly effect, the study of chaotic dynamical systems has also been incorporated into other scientific fields throughout the last years. And although in the current worldwide situation, I think that we have noticed some kinds of butterfly effects within the last month. Now, in mathematics, there are several precise definitions of chaos or chaotical dynamical systems. Although I think there's no standard definition of chaos in mathematics, one of these definitions has become quite commonly used throughout the last years, and it's due to Diveni in 1989. And one part of the definition of Diveni chaos is the following. So what follows now is not the complete definition of Diveni chaos, it's only one part of the definition. And this part of the definition is the following. We consider here a continuous dynamical system, which means topological space X and a continuous self-map T of X. And then the map T, or also the dynamical system XT, is called transitive or topologically transitive if for all non-empty open subsets U and V of X, there is some integer n such that the intersection of the image Tn of U and V is not empty. How can we imagine this behavior? So here is an idea. So it's only a schematic block, so very easy example. So it's to generalize this. It's just to get some idea what transitivity means. So whenever we have one empty open subsets U and V, we have to find so that the map T is transitive. We have to find a point in U, which after finitely many actions of the map T, eventually is mapped into the open set V. Finitely many iterations of the map T. And of course, this should not only be the case for this open set U and V, but for all pairs of non-empty open subsets of X. So one can imagine it's kind of a mess if one would like to draw it into this picture here. So it's a quite wide behavior of the dynamical system. As already said, this is not the complete definition of Diveni chaos. There are, at first view, other parts or other properties. The second property of Diveni chaos is quite a contrary property, namely that there exists a dense set of periodic points of T. So a periodic point of T is a point which, after finitely many iterations of T, is mapped to itself again. which means that the existence of a dense set of periodic points means, in contrast to a wild behavior, some very chain behavior. And then there's a third property in Divenius' definition of chaos, which is called sensitive dependence on initial conditions, which somehow formalizes the butterfly effect I have mentioned before. I don't want to go into the details here. And then very interestingly, it turned out, so it was shown, that the first two properties, namely transitivity and the existence of a dense set of periodic points, already imply this sensitive dependence on initial conditions, which means that when we consider transitivity here, we can say that this is half of the definition of Diveni chaos, and even more interestingly, it's the wild half of the definition of Diveni chaos. And in this talk, we will be mainly interested in some special cases of transitive dynamical systems. Now, the talk is not called transitivity, but simultaneous hypercyclicity. So what is hypercyclicity and what about its link to transitivity? It's like this. So first, the definition of hypercyclicity. So again, we consider a continuous dynamical system, Tx, and then the map T is called hypercyclic. Whenever there exists a point x0 and x, such that the orbit of x0 under T is dense in x. So the orbit of x0 under T is the set of iterates Tn of x0, ends with the positive integers. And if this set is dense in x, we call the map T hypercyclic. And moreover, in this case, the point x0 is also called hypercyclic for T. And for the notation, we write hc of T for the set of all hypercyclic elements for T. Clearly, in case of hypercyclicity, the set, the topological space X must be separable, so there must be countable and dense subset. In particular, each orbit on the hypercyclic element is countable and dense in X. In other words, this means if x0 is hypercyclic for T, this means that for each point y and x can be approximated via a subsequence T and K of x0. So this is hypercyclicity. And we will only be interested in more specialized settings. So we will be interested in the linear setting in the following, which means that throughout the talk, we will be considered in the case that X is a topological vector space and that T is an operator on X, which means that T is a linear and continuous self-matrix. For instance, we will be interested in the space H of C, the space of all entire functions, and here we will consider operators of the following form. So, for instance, we will consider translation operators now A, which map an entire function f to f, but shift the argument by A. And similarly, we will be interested also in differentiation operators D. So the differentiation operator D maps an entire function to its derivative. As usual, the space of entire functions will be endowed with a topology of locally uniform convergence, such that it becomes a Fréchet space. And it's a separable space because, for instance, the polynomials with certain rational coefficients are countable and dense in H of C. Another setting where we will be interested in are the sequence spaces RQ. And here we will be interested in operators called backward shift. So backward shift B simply maps an element of a sequence space to the sequence, but the first entry is deleted. So the first entry is cut. This operator is called the backward shift. And here we have even a Banner space, LQ. And the LQs are also separable because, for instance, the finite sequences, so the sequences ending with 0 with Gaussian rational coefficients are countable and dense. Now, this is a definition of hypercyclicity. Now, what about the link between transitivity, which we hadn't considered before, and hypercyclicity? It's like this. Indeed, it's the theorem, and it's called Birkhoff's transitivity theorem. I think in its earliest form, it's from around the 1920s. Maybe not in this general form here, but I think the beginning was at the 1920s. So what do we consider here? We consider here a separable Fréchet space X and an operator T on X. So Birkhoff's transitivity theorem could be formulated under weaker conditions. So, but since we will be only interested in Fréchet spaces and examples, I put this conditions here. And then the theorem says the following. An operator T is hypercyclic exactly when it's transitive. And moreover, in this case, the set of all hypercyclic elements or hypercyclic vectors for T is a topologically very large set, namely a dense G-delta set. It is well known that, for instance, non-identity translation operators or the differentiation operator are hypercyclic on the space of entire functions. And also, it is known that weighted backward shifts lambda b are hypercyclic on the sequence spaces whenever the modulus of the weight is greater than 1. And in fact, only for these weights with modulus greater than 1. Now, the proof of Birkhoff's transitivity theorem mainly uses Baer's theorem in the form that on complete spaces, a countable intersection of open and dense sets is dense again. And for this reason, we obtain this existence statement. So we obtain hypercyclicity is equivalent to transitivity. And in this case, there exists a large set, a dense G-delta set of hypercyclic elements for T. But at first view, we don't have any concrete information of the set of hypercyclic elements for T. We know it's topologically large, but we don't know any of the hypercyclic elements precisely in the first place. And not only in the first place, I think throughout the whole theory of hypercyclic operators, nearly no concrete examples of hypercyclic elements are known. There are a few exceptions. For instance, the Riemann zeta function fulfills some kind of special translation cyclicity on the right half of the critical strip. But also there, we don't have an explicit presentation of the Riemann zeta function. So, for instance, let's have a closer look at hypercyclicity of the differentiation operator D. So we know it's hypercyclic. So Birkhoff's transitivity theorem says that there exists a dense G-delta set of entire functions which are hypercyclic for the differentiation operator. This means whenever we take such a hypercyclic function for the differentiation operator, we can see all other entire functions just by looking at its derivatives. Or in other words, each entire function can be approximated by the derivatives of a hypercyclic function of the differentiation operator. And this is not, it does not only exist one of such hypercyclic functions for the differentiation operator, it's already the topologically normal, or let's say generic case. But which hypercyclic functions, with which entire functions do we know, or do we think we know? I think first one might think about polynomials. But clearly, the orbit of a polynomial under the differential operator, this is a finite set, so its cardinality is the polynomial. Or even more dramatically, take the exponential function, then the orbit under the differential operator is only a singleton, so it's far away from being dense in the entire function, in the space of entire functions. So it's a bit like looking into the sky at night. Everything we see are the stars which shine. So in case of the differentiation operator, the entire functions we know, but which hypercyclic for the differentiation operator. But all the dark matter around the stars, we know it's there, but we don't have some explicit representation of the dark matter. We only know it's there. And it's the same for all the entire functions which are hypercyclic for the differentiation operator. So due to Birkhoff's transitivity theorem, we know that they exist, but this is a normal case. We don't have any special information about them. And at least for me, this is one point which makes this whole theory of hypercyclic operators so interesting. Now, so we have clarified the link between hypercyclicity and transitivity. So what about our new concept of simultaneous hypercyclicity? The motivation is as follows. We consider again a separable Fauché space X, and now two operators T and S on X, which we assume to be hypercyclic. Then, due to Birkhoff's transitivity theorem, we know that the set of hypercyclic elements, both for T and for S, are those dense G delta sets, and in particular, the intersection is not empty, which means we can find a point x0, which is both hypercyclic for T and for S. In other words, this means the following. This means that for each point y in X, there exists a strictly increasing sequence nk of positive integers, such that T and k of x0 converges to y, and analogously, there exists a strictly increasing sequence mk of positive integers, such that the smk's of x0 converge to y. And Luis and me, we were interested now in the following question, namely, under what further conditions on the operators T and S can we guarantee that there's a point x0 in X such that for each point y in X, there's one sequence nk such that both T nk of x0 and S nk of x0 converge to y. So using the same subsequence. And this will lead us to the definition of simultaneous hypercyclicity. So it's like this. We consider X topological vector space, and we assume that it has a Hausdorff property. And now we consider finitely many operators on X, not only two, but finitely many, and we denote them by T1 to Tp. And then T1 to Dp are called simultaneous hypercyclic, or in short, s-hypercyclic, if there exists some point x0, so that for each point y in X, there is one strictly increasing sequence nk of positive integers, such that all the tj and k of x0 converge to y for k towards infinity. And moreover, we say that the p operators T1 to Tp are densely s-hypercyclic if the set of all s-hypercyclic vectors for them is dense in X. So an s-hypercyclic vector for T1 to Tp is the point x0 fulfills the property in the above definition. So densely s-hypercyclic means that exists a dense set of s-hypercyclic vectors. Of course, we were not the first ones who were interested in hypercyclicity concepts of one operator. So there are some related concepts, or let's say at least I was not the first one who was interested in something like this. So there's a related concept due to Bernal and Paris independently from each other from 2007. And it's called disjoint hypercyclicity. Under the same conditions of the above definitions, the operators are called disjoint hypercyclic, or in short, d-hypercyclic, if there exists some point x0, such that now for each p tuple, y1 to yp in the product xp, there is one sequence nk such that the tj and k of x0s converges to the j's entry, so to yj for all j between 1 and p. Another related concept is maybe the hypercyclicity of the direct sum of the operators T1 to Tp, so the direct sum of the operators map tuple x1 to xp to the tuple T1 x1 to Tp xp. I think in this general form, there's not really a name for this kind of hypercyclicity. I will refer to plus hypercyclicity in the following slides when I want to speak about this. Only in case of p equals 2 and t1 equals t2, so we have one operator t and consider the direct sum t plus t, then we also speak about that the operator t is weakly mixing, and then we have a whole theory of results for this. And similarly for the hypercyclicity, Bernal and Paris, they also proved many results or conditions under which the operators are disjoint hypercyclic. Let's compare these concepts. So by definition, disjoint hypercyclicity of the operators T1 to Tp is stronger both than simultaneous hypercyclicity and plus hypercyclicity. So it's simply by definition. So if I go back one slide, if the operators are disjoint hypercyclic, this means I can approximate each p tuple with some hypercyclic element x0, and then clearly I can approximate each single point with the same subsequence. So this means the d hypercyclicity is stronger than s hypercyclicity, and also when I can make each p tuple with one vector x0 and the same subsequence, then clearly I can also approximate each p tuple with the hypercyclic p tuple x0, x0 to x0, so only with entries x0, which means that d hypercyclicity is also stronger than plus hypercyclicity. And also trivially, or by definition, both simultaneous hypercyclicity and plus hypercyclicity of the operators T1 to Tp imply that each single operator is hypercyclic. So I think this is clear. Now, a bit more interesting is the following relation. If you consider a hypercyclic operator T, then clearly the pair TT is simultaneous hypercyclic, just by definition, but not disjoint hypercyclic. So why it's not hypercyclic? In this case, there would be some disjoint hypercyclic vector x0, which means we could approximate all tuples or all pairs in x2. But if you take distinct points y1 and y2, clearly we cannot approximate them with the same subsequence. Because we are on a host of topological vector space, and then we have unique limits of sequences. Some further comparisons. If you consider weighted backward shifts again on the sequence spaces IQ, for example, 2 times the backward shift and 4 times the backward shift, then these are hypercyclic, as I already mentioned. But clearly, or more or less clearly, these two operators are not simultaneous hypercyclic, because if I take some subsequence nk of positive integers, and 2 to the nk and 4 to the nk, they have different speeds of increasement, so it's not possible to approximate the same element with them. Maybe this is a heuristic argument here, but later on we will see a precise theorem about simultaneous hypercyclicity of scalar multiples of one operator. Then also the following holds. It is well known that 2 times the backward shifts and 4 times the backward shifts of this pair is even hypercyclic on the sequence spaces LQ. So this means we have here an example of a pair of operators which are plus hypercyclic but not simultaneous hypercyclic. And also there are examples for the other way around, namely of operators which are simultaneous hypercyclic but not plus hypercyclic. And for instance, this is due to the famous De La Rosa-Reed theorem from 2009, who showed that there even exists a Banach space X and a hypercyclic operator T on X, such that T plus T is not hypercyclic on X2, which means that the pair TT is not plus hypercyclic, but as we have seen above, it's clearly a simultaneous hypercyclic. So all in all, this means that besides the first two trivial points by definition, all the other relationships between S, D, and plus hypercyclicity, they are not clear at first view. And we were mainly interested in finding examples of operators which are simultaneous hypercyclic, but not disjoint hypercyclic. So we want to find concrete examples, operators of, or let's say, non-trivial examples of operators being S, but not d-hypercyclic. And this is what we want to do in the following slides of this talk. Okay. As in case of hypercyclicity of one operator, there's also a link between simultaneous hypercyclicity and a property which we call simultaneous transitivity. In order to formulate this, let's have a quick reminder that we call a self-map T transitive on X if for all non-empty open subsets U and V of X, there exists some integer n such that the intersection of the image Tn of U and V is not empty, which is indeed equivalent to the fact that the intersection of U and T minus n of V is not empty. So this is a very loose notation here. So T minus n of V should denote here the pre-image of V under the map Tn. So it's not an inverse function. We don't have bijectivity here in general. So it's simply the pre-image of V under the map Tn. Then in this spirit, we define simultaneous transitivity as follows. So we consider P operators, T1 to Tp, and we call them simultaneous transitive, or in short, S-transitive, if for all non-empty open subsets U and V of X, there exists some integer n such that the intersection of U with the intersection of all pre-images Tj minus n of V is non-empty. So it's kind of an enhancement of the definition for the normal transitivity case. And using this definition analogously to the Birkhoff's transitivity theorem, we were able to prove this theorem, which we call the S-transitivity theorem. So we consider a separable Fouché space X and P operators T1 to Tp on X. And then we proved that these operators are densely simultaneous hypercyclic if and only if they are simultaneous transitive. And moreover, also as in case of Birkhoff's transitivity theorem, in this case, the set of all simultaneous hypercyclic vectors for the operators to T1 to Tp is a dense G delta set. So the proof works quite similar as the one of Birkhoff's transitivity theorem. It mainly uses Baer's theorem, and okay, we obtain a similar theorem for the s-hypercyclicity. Now, using this S-transitivity theorem, we were able to show that certain p-tuples of translation operators are simultaneous hypercyclic on the space of entire functions. We will see details for this later on after some slides. But for other examples, such as differentiation operators or weighted backward shifts, we were not able to find examples of them being S but not D hypercyclic by only using this S-transitivity theorem. And for this reason, and I think also out of some, let's say, intrinsic motivation, we were looking for further tools for proving s-hypercyclicity of operators. Now, in case of a single operator, the following criterion is well known for proving hypercyclicity. So it's called the Hypercyclicity Criterion. I think in this form I stated it here. It's from 1999 to Base Paris. There exists some earlier versions. I think the first one was from the beginning of the 1980s. It's called a Kitai criterion, and there's also a Gethner-Shapiro criterion earlier than this 1999 criterion. But they have a little bit stronger assumptions. So I think with these assumptions, it's from Base Paris in 1999, and it says the following. If you consider a separable Fouché space X and an operator T on X, and strictly increasing sequence nk of positive integers, as well as dense subsets x0 and y0 of x, and mappings, or a sequence of mappings, sk, mapping from y0 to x. So just arbitrary mappings, don't need to be continuous, don't need to be linear, such that the following three conditions are fulfilled. Namely, on x0, we have pointwise convergence of the t and k's to 0. On y0, we have pointwise convergence of the s and sk's to 0. And also on y0, the composition of the t and k and sk's also converges to 0 pointwise. If all these conditions are fulfilled, then the operator t is weakly mixing, or in our notation, t plus t is hypercyclic. So in particular, t is hypercyclic. And Luis and me, we were able to find a similar criterion, for simultaneous hypercyclicity. And at least for me, this is maybe the, let's say, the most interesting result of our work. And the following. So with the s-Hypercyclicity criterion, again, we consider a separable Fouché space X, and now P operators T1 to Tp. Now we assume that the following exists. A strictly increasing sequence nk of positive integers, a dense subset x0 of x, and a subset w0 of the product xp, such that the diagonal of xp, so the set of all p tuples with only the same entries, this should be contained in the closure of the set w0s. And then we require the existence of a sequence of mappings rk from w0 to x, such that also three conditions should be fulfilled, similarly to the hypercyclicity criterion. First is that all the tj nks converge to 0 pointwise on x0. Then the second is that the rks converge to 0 pointwise on w0. And the last condition is that for each point w in w0, so w is then a p tuple consisting of entries w1 to wp, and then the composition of tj, nk, and rk of w converges to a point in the convex hull of the single entries of the point w. If all, and this for all j, so for all j between 1 and p. And if all these conditions are fulfilled, then we proved that the operators T1 to Tp are densely simultaneous hypercyclic. Now, although I'm out of mathematics for around 3 years now, I still remember one wisdom concerning mathematical talks, namely that a good mathematical talk should contain at least one proof and one joke, and that these two things should not be the same optimally. Now, since this s-Hypercyclicity criterion is our major tool for proving simultaneous hypercyclicity in concrete situations, and since its proof is surprisingly easy, I thought this would be a good point in my talk for presenting at least the required proof. So let's have a short look at this. So we want to show that under these conditions, 1, 2, 3, operators T1 to Tp are densely simultaneous hypercyclic. And we will do this by showing that the operators are simultaneous transitive, because then our s-transitivity theorem implies that they are s-hypercyclic. Now, in order to show that under these conditions, the operators T1 to Tp are s-transitive, we fix a pair of non-open empty subsets u and v of x. And now the following holds. Since the set x0 in the second line of the assumption is assumed to be dense, we can find a point x0 in the intersection of u and x0, and we take some arbitrary point y0 of the set v. Now, due to the local convexity property of our Fouché space X, There's an open and convex subset V tilde of X, which is contained in V and which contains the point Y0. So in fact, this is the first time that we use that we have that X is a Fauché space, or that we use the local convexity of Fauché spaces. In fact, all previous results, also the s-Transitivity theorem, they also hold without local convexity. So they hold, for instance, on separable, completely metrizable topological vector spaces. Now we have a local convexity, so we can find such a set V tilde. And now, due to the assumption, the one assumption was that the diagonal of XP is contained in the closure of W0. So since the tuple Y0 to Y0 is in the diagonal, so it's in the closure of W0, we can find a point W with entries W1 to WP in V0, such that all the entries Wj are in V tilde for all j. Now we define a sequence, set K, namely our point X0 plus Rk of W. And for this sequence, the following holds. So the second of the assumption was that the Rk's converge to 0 on W0, which means that the set case converge to X0. And now if you consider the Tj nk of set case, due to linearity, we can split it up into summands. Now due to the first condition, the Tj nk converge to 0, so the first summoned converge to 0, and the composition of Tj nk and Rk of W, this converges for each j due to the assumption to a point which I denote here by Yj, and this point is in the convex hull of the set of the entries of W, so in the convex hull of W1 to WP. So in particular in the convex hull of V tilde, but since V tilde is convex, this is V tilde and this is contained in V. This means we have shown the following. The set case converge, or the sequence set K converges to 0, which is contained in the open set U, and the sequence Tj nk of set K for each j converges to a point Yj, which is in the open set V. Which means that for k large enough, eventually, the set case are in the intersection of U and the intersection of all the Tj minus nk of V. Which means that we have shown that the operators are simultaneous transitive, and then our s-Transitivity theorem implies that the operators are densely simultaneous hypercyclic as required. Okay. Now, before we proceed with further results of s-Hypercyclicity, I want to give some more background information about hypercyclicity criteria. First, in case of a single operator. The hypercyclicity criterion I showed you, of course, it was not false, it was correct, but it was not the whole truth. So the whole truth, or at least some more truth, is here. Namely, Paris, they showed in 1999 that if an operator T satisfies the hypercyclicity criterion, so this means satisfies the assumptions of the hypercyclicity criterion, then this does not only imply that T plus T is hypercyclic, but it's also the other way around. It's an equivalence. And moreover, they showed that a condition is equivalent to these first two conditions. Namely, the condition that there exists some sequence nk of positive integers, such that for each subsequence mk of nk, there is some point x0, such that the orbit of x0 under the tm case is dense in x. So, of course, this is a stronger property than mere hypercyclicity, because smaller orbits have to be dense. This has also named this property. It is called that the operator T is hereditarily hypercyclic with respect to the sequence mk. So now I pay here a little bit surprised that I did not introduce this definition at the beginning, but there I did not want to have an overload of definitions. That's why I put it just here in the theorem. Then, such a context of the hypercyclicity criterion also holds in case of disjoint hypercyclicity. So this is again due to Paris from 2007. they consider a separable Fouché space X and P operators T1 to Tp, and they show that the following are equivalent. The first A is that the operators satisfy a so-called disjoint hypercyclicity criterion. I put it in apostrophes here because I did not define this. So this is a similar criterion than our s-Hypercyclicity criterion, but with stronger assumptions, which then imply that the operators, if they fulfill the stronger assumptions, are disjoint hypercyclic, but very similar to our s-Hypercyclicity criterion. And then base pairs showed that this is equivalent to the fact that for each positive integer m, the m-fold direct self-sums of the operators T1 to Tp are so-called disjoint transitive on xm. Also put it in apostrophes here because I did not define it. The definition of disjoint transitivity is also very similar to our definition of S-transitivity, only in the definition not only one open set V, but P open sets V1 to Vp are considered. And moreover, they showed that these two conditions or properties are equivalent to a third one, which we might call hereditarily disjoint hypercyclicity, namely that there exists a sequence mk such that for each subsequence mk of it, there is some point x0 such that the joint orbit of the operators is dense and the product xp. So maybe you ask yourself, why do I tell you all this stuff? Not only to fill up my slides, also, but not only, but mainly because we found some similar equivalences for our s-hypercyclicity criterion, which somehow demonstrates that the assumptions we require in our s-hypercyclicity criterion are quite natural and fit into the whole landscape of hypercyclicity criteria. Namely, we proved the following statement. So again, we consider X a separable Fouché space and P operators, T1 to Tp, and then we proved that the following are equivalent. The first condition is the operators T1 to Tp satisfy the assumptions of our s-hypercyclicity criterion, and we proved that this is equivalent to the fact that for each positive integer m, the m-fold direct self-sums of the operators are simultaneous transitive. And a third property, which we have called hereditarily simultaneous hypercyclicity, namely that there exists some sequence nk such that for each subsequence nk, there is a point x0 such that the joint orbit or the closure of the joint orbit contains the diagonal of xp. And in addition, we were able to prove the following. Whenever there is one operator among the P operators which commutes with all others, then already the simultaneous transitivity of twofold self-sums, so simultaneous transitivity of T1 plus T1 to Tp plus to Tp already implies the simultaneous hypercyclicity criterion is fulfilled. So, so far about some background about hypercyclicity criteria. Now let's proceed with some further results of simultaneous hypercyclicity. I think I have already mentioned quite at the beginning that an operator T can never be disjoint hypercyclic with itself. And even more, the following holds due to an argument by Esta from 2007. They showed that an operator can never be disjoint hypercyclic with a scalar multiple of itself. But for simultaneous hypercyclicity, some more similarity among the operators is allowed. So we proved the following. Consider again Fouché space X and now operators T and T1 to Tp and X and scalars lambda1 to lambda P. So first, necessary condition. So if all these operators are simultaneous hypercyclic, then it must be the case that all the scalars are unimodular. Moreover, we were able to find a sufficient condition for simultaneous hypercyclicity. It's this one. So if all scalars are unimodular And if now for each strictly increasing sequence nk of positive integers, there's some point x0 such that the orbit of x0 under the Tn case is dense in x, then we proved that the operators T, lambda 1, T1 to lambda P, Tp are densely simultaneous hypercyclic. So this property also has a name. Sometimes it's called that the operator T is hereditarily hypercyclic with respect to the full sequence. Though at first view, this is quite of a hard assumption, because now for each strictly increasing sequence nk, so could be a very sparse sequence or a very fast increasing sequence, or we have to find dense orbits. And okay, it is a hard condition, but it is well known that this condition, this hereditarily hypercyclicity with respect to the full sequence, is indeed fulfilled for all the three standard examples. So for translation operators, differentiation operators, and weighted backward shifts, which means that we obtain now first examples of operators which are simultaneous but not disjoint hypercyclic. So for instance, due to our theorem and due to the fact that an operator can never be disjoint hypercyclic with a scalar multiple of itself, we obtain, for instance, that non-identity translation operators and the negative are simultaneous but not disjoint hypercyclic on the space of entire functions. And similarly, we obtain that the differentiation operator and minus the differentiation operator are s but not d hypercyclic on the space of entire functions. And also we obtain that weighted backward shifts, for instance, 2 times the backward shift and minus 2 times the backward shifts, are s but not d hypercyclic on the sequence spaces IQ. So this is quite nice as a starting point. But of course, we were interested in finding some more advanced examples or some more non-trivial advanced examples of operators which are simultaneous but not disjoint hypercyclic. And indeed, we were able to find such cases for all the three standard examples, so for translation, differentiation operators, and weighted backward shifts. So let's start with the translation operators. Due to Bernal and Base-Torres in 2007, the following is well known. Whenever we have p pairwise distinct points, a1 to ap of the complex plane, not zero, then the corresponding translation operators tau a1 to tau ap are densely disjoint hypercyclic on the space of entire functions. Now we were able to prove the following slight extension. We consider here again p points a1 to ap non-zero, but now they don't need to be necessarily pairwise distinct. And we consider p scalars lambda 1 to lambda p with the property that whenever there are two indexes j and l such that aj equals al, then the modulus of the corresponding lambdas, the modulus are the same. And if this condition holds, then we showed that the weighted translation operators lambda 1 tau a1 to lambda p tau ap are densely simultaneous cyclic on the space of entire functions. As already said, for proving this, we used our s-transitivity theorem. So we did not have to use the s-Hypercyclicity criterion here. And also we used Runge's theorem on polynomial approximation. So the proof is quite similar to the proof that a single translation operator is hypercyclic. For instance, we obtain now examples of the following form. So for example, 2 times the translation operator shift by 1 and the translation operator shift by 2 and minus the translation operator shift by 2 are simultaneous hypercyclic but not disjoint hypercyclic on the space of entire functions. So let's consider the next example. Now the differentiation operators. So again, due to Bernal and Base-Torres in 2007, the following is well known. Whenever we have p integers r1 to rp strictly increasing and p scalars non-zero lambda 1 to lambda p, then the weighted differential operators lambda 1 dr1 to lambda p drp are densely disjoint hypercyclic on the space of entire functions. We proved the following slight extension. We also consider p integers R1 to Rp, not necessarily increasing, and non-zero scalars lambda1 to lambda p. And if they fulfill the conditions that whenever we have indexes j and l such that rj equals rl, then the modulus of the corresponding lambdas is the same, then the weighted differential operators are densely simultaneous hypercyclic on the space of entire functions. Here, we were not able to do this with our only the s-transitivity theorem. So here, at least, we had to use our s-hypercyclicity criterion for proving this statement. And for instance, we obtained that this example, so 5 times the differential operator and d square and minus d square. This is an example of a triple of operators which is simultaneous hypercyclic, but not disjoint hypercyclic on the space of entire functions. Last example. Due to Bayes Paris in 2007, the following is known. We have p integers R1 to Rp and p scalars lambda1 to lambda p. And then the weighted backward shifts lambda1 br1 to lambda p brp are densely disjoint hypercyclic on the sequence spaces IQ, exactly if the sequence or the finite sequence of integers is strictly increasing. And the same also holds for the finite sequence of modulus of the scalars, and all of them are greater than 1, because this is a necessary condition for even obtain hypercyclicity. We proved the following. So we also consider p integers R1 to Rp and p scalars lambda1 to lambda p. And then in this proposition, I consider here a set A. This is a set of all indexes j such that Rj equals Rj plus 1. And then we consider 3 conditions. The first is that the modulus of all lambdas are greater than 1. The second is that for all indexes which are not in this set A, the modulus of lambda j is strictly smaller than the modulus of lambda j plus 1. And the third condition is that for all indexes j in the set A, we have equality of the modulus of lambda j and lambda j plus 1. And then we proved that the weighted backward shifts are densely simultaneous hypercyclic on the sequence spaces exactly when all these 3 conditions hold. Again, we used our simultaneous hypercyclicity criterion to show this statement. And for instance, we obtained that 2 times the backward shift, 3b square and minus 3b square. This is an example of operators being simultaneous hypercyclic, but not disjoint hypercyclic on the sequence space. So we have seen some, let's say, not very trivial examples of operators being simultaneous but not disjoint hypercyclic. But of course, in this context, a natural question comes up, namely this one. So we consider p operators on a separable Fichet space, and we assume that they are s-hypercyclic. Now, the natural question is, under which further conditions are they already disjoint hypercyclic? So I want to mention 2 approaches here. The first one is due to the referee of our paper. So the referee of our paper had some good reasoning that if there is a point x0 and x and a co-finite dimensional subset f of the product xp, which is contained in the closure of the joint orbit, then this might already imply that the operators are already disjoint hypercyclic. Frankly speaking, I don't understand this in detail anymore, but I think it is a very good reasoning, and it's also mentioned in our paper. That's why I want to mention it here too. But then there's another approach to this open question, which I have to say, unfortunately, I still remember. Namely, all examples of tuples of operators which we have seen, which are simultaneous but not disjoint hypercyclic, they contained at least 1 pair of operators which are scalar multiples. So a justified question might be, if we have s-hypercyclic operators and none of them are scalar multiples, are they maybe already disjoint hypercyclic? Personally, I hope that this is not the case, because it would somehow reduce our concept of simultaneous hypercyclicity. But however, we were not able to find other examples. So this is now more or less the end of my talk. More or less, because some minutes ago I told you that a good mathematical talk should contain at least one proof and one joke, and that these two things should not be the same optimally. So I gave you one proof, but no joke so far, or at least I hope my proof was not a joke. But since I was not able to incorporate a joke in this talk, I want to give you a second proof, alternatively. But don't worry, it's a very short one, and it's a bit off topic. And in order to give you this second proof, I want to state one last theorem. It's this one. My time in Sevilla was amazing. So hereby, I want to express my gratitude to Luis. You always made me feel welcome. You spent so much time with me, and it was really a pleasure and honor to work with you together. Muchas gracias. And also thanks a lot to Carmen, I don't know if she's here, and Jose for all these nice mathematical and non-mathematical conversations during, before, and after coffee breaks. So now the second proof. So a very short one. So it's this one. So, pues bien, una imagen vale más que mil palabras. So only a few words. Not only me, but also my wife liked it so much in Sevilla when she came to visit me during my stay there. And that's why we decided to get married there. And this is a picture of the two of us at our wedding at Basilica de la Macarena last year. Now, the very end of my talk, returning to mathematics. So here are the main references of this talk. So Pablo, thank you very much for organizing this talk. It was a real pleasure to think about some mathematical things again after some years. Muchas gracias. And of course, thank you very much to all of you for listening to my talk. Yeah, muchas gracias. ¿Algunas preguntas?
So thank you very much, Andreas, for your talk. I think the last theorem is the one I best understood. I hope it's not the case for the rest of the people that attended. So if anyone has any questions, feel free to ask. And yeah, that's all I wanted to say. Okay, Jürgen and Luis, I don't know if they can turn on their microphones. Can you try, Luis? I'm unsure. If not, I'm turning you into moderator. So can you ask now, Jürgen, a question? And also, Luis, are you now able to turn on your microphones and ask the questions, please?
Now?
Yes.
Now, just to say hello and my congratulations to Andreas and all the audience, and the theorem I prefer is the last one. All the pleasure is for me, and muchos abrazos. The talk has been interesting even for me. Okay, muchos abrazos, Andreas, and all the audience.
Gracias.
Para ti.
Hasta
luego. Gracias.
And Jürgen? I'm unsure if Jürgen can turn on its microphone or...
Okay, yeah. Now?
Yes, yes.
Okay, I also wanted just to say thank you very much for giving me the possibility to be here, a part of this nice seminar, and it was a very nice talk. Thanks to Andreas, and it was a great pleasure to meet you again, at least in this way.
Yeah.
Hopefully in the future we will meet again personally.
Yeah, same for me, Jürgen.
Yeah. Okay. So goodbye.
Thank you very much, Jürgen. So if no one has further questions, we just want to thank the speaker again. Thank you very much, Andrea. And we will
Thank you to all of you.
session now. Have a good day.